So many people look at the progress of human technologies as a series of ages of different materials. So for example, we all know about the Stone Age, the Bronze Age, and the Iron Age. Where I think we're going is a new age. Let's call it the age of molecularly engineered materials.
The new approach that people talk about now in the field is this incorporation of data sciences with computational methods as well as experimentation. And so this is something that's relatively new.
There have been major advances in computational methods for starting with a molecule and predicting what the properties will be. So that's very important. But it turns out what you really want is you want to be able to design the molecule to give you the desired properties. And that's where machine learning comes in. So machine learning has figured out ways of solving very difficult optimization problems. And so what we can do is we can take that computational model, integrate it to a machine learning algorithm, and then have it search for molecules of the right characteristics to give us the desired properties.
So the project we're working on with the National Science Foundation is designing materials to engineer and revolutionize our future. So this project is designed to discover new additives that can be added to polymers in order to improve their properties by designing them to have new kinds of microstructures. So for example, if we can design an additive that will change the microstructure of the polymer so that it has better strength to weight ratio or better optical clarity, this will translate into better performance and applications in the real world. So that's what we're trying to do with this particular project. The way we do it follows the paradigm of the Materials Genome Initiative, which is how the combination of computer science and data informatics and characterization and experiments in the laboratory can work together to advance materials discovery.
My primary role on the DMREF project was the person who built the tools to run the simulations and to analyze the results from the simulations to understand how nucleation proceeds on a surface. In the center of the video, we have a representation of a graphene nanoplatelet. So that's the surface where the nucleus of the crystallizing material starts. And at the beginning of the video, you can see just melted amorphous material, but over time, you develop a nucleus which forms on the surface and eventually grows and propagates a growth front of a crystallizing polymer material.
So computational methods are really important to projects like DMREF because they let us take a look at systems that we can't see experimentally. They're too small or they're too fast. Computation allows us a chance to get down to those length scales and time scales so that we can actually understand the fundamental mechanisms of what's going on.
I use experiments to validate what simulations can tell us about the nanoscale nucleation event, and we can see how that propagates into a real material. Well, I have a video here of what a typical experiment looks like. I've sprayed hundreds of micron-sized droplets of polyethylene onto a clean nucleating agent surface, and then what you see is these melted droplets now being quenched down to a cool temperature and crystallizing. And so what you can see in the image on the left are these hundreds of droplets that originally start dark, and then as they crystallize, you'll see them appear as red droplets. What's significant about this video is we have hundreds of independent nucleation events all occurring at once, and so it allows us to investigate something that's stochastic and a rare event in hundreds of droplets so that we can get good statistics to pull out information about what's actually occurring.
There have been major advances in computational science, but what's important to society is to translate those advances in computational science into materials and products that create jobs.
GOALI, which is another part of our projects, is the grant opportunities for academic liaisons with industry. This is the mechanism by which the National Science Foundation stimulates collaborations between academic researchers like ourselves and industrial collaborators.
So our collaboration with ExxonMobil it's a two-way street. They do experimental validation of anything that we propose, testing of new additives, and in return we develop new tools for them and suggest new research directions.
Particularly for ExxonMobil, we have over the years been heavily focused on experimentation. And so most of what we do I consider to be very Edisonian. The ability to incorporate computational sciences and data-driven methods, which this program is all about, will truly represent a paradigm shift in the way we do the science and product development. We're also able to bring in the interns, and this is very valuable for us specifically in terms of looking at candidates. But even if we don't hire them, this is a way of training the future scientists and technologists that will go into be part of American industry.
So MIT's, the whole culture is about innovation. And everyone here is trying to push that innovation forward. And MIT really encourages that. They want the students and the researchers to find the new science of tomorrow that will push forward technology and make life better for everyone.